Okay, so this is our last session before your exam, and this session is not going to be like the others. It's going to be shorter, I guess, because we're going to have just one presentation to go through. There's not going to be an exercise session, but if any of you have any kind of questions, then of course I'm here to answer. One thing that I wanted to mention about the exam, you've seen the site is up, right? The BG Coder. One thing that wasn't 100% clear to me from the requirements document on the sample exam is that you're actually submitting one task each time, right? And you're submitting your main CS file. So you have to contain all your code in one place, and then you're just pasting it and submitting it here. And it runs through a series of tests, which you can see after that your results and see if you've been successful or not. So this is one successful submission, and this one is unsuccessful, and this one is still waiting. And I think there is something in the queue here that stops everything. This one is processing for quite some time, but I've submitted another trial here which is still in queue for quite some time. So in case the system hasn't crashed, you can submit and you can see your results quite fast. It's good and bad because you can see if you did well or not while you're submitting, and you can correct yourself and you can resubmit, but it's bad because you can do that. So just so you know, it wasn't very clear to me in the document because it said all the code must be in one document, but actually it's delimited into different tasks, and I think this site works well when it works, and it's quite intuitive, so you can use it. Okay, today we're going to talk a little bit more about methodology of problem solving in relation to your exam and not in relation to your exam. We'll try to see how the process of taking a problem and putting it into a software solution works in a kind of a broken down way. Of course, this is not everything there is to know about it, and many of this process is up to you and the way that you resolve problems. There are whole books about solving certain problems, and for example, one thing that I know in person is that if you take, for example, Microsoft as a corporation, as a company that hires people, it is a known fact that Bill Gates is a big fan of riddles and logical questions, and it is known that in their interviews they would come up with questions that will shock you completely. And there's a whole book which is called How Do You Move Mount Fuji? And that's one of the questions in their interviews, by the way. And this book is dedicated only to questions asked in Microsoft interviews and how to resolve them and how to approach them. And one tip which is always accented in such context is always keep thinking about it. Always try to make it simple. Always try, if you are, for example, in an interview scenario, and in such case, especially if you are going to Microsoft or Google or any of the big companies, it's always process. If you are shocked by a question, like for example, how many gas stations are in California, which is something they can also ask according to that book, they want to shock you and they want to see your reaction, but they want to see how you take it and logically start breaking it down and how your mind works. So all the time talk, all the time try in your mind to break down a problem. So we'll see a little bit about the process in resolving a certain problem, and we'll see how it's broken down and how the code is constructed. and you can feel free to ask relevant or irrelevant questions during. So, of course, the first thing is to understand what you're facing. If you're facing a problem that you have to resolve in code, the first process starts in your head, and you have to fully understand the requirements. And that's not only true for code questions or exams, it's true for the life of the developer. Whenever there's a new feature, whenever there's a new requirement, whenever there's some bug to fix, but it's actually a change of the product in any behavior, ask questions and always get to understand exactly what is required from you. Because if you implement something and then it's actually not what you needed to implement, then you have to redo the whole process. Paper and sketching always works. If you are in an exam, it's always good to have it. It's better to have a whiteboard, and usually in discussions of new features and working on new things, the whiteboard is a big star, and it's usually very helpful to visualize things if you're using classes, to see how they are distributed, what's affecting what. If you're planning a database, try to see how your tables interact, which modules affect which. So that's always good. And if you're building your algorithm, it's always good to see. We'll see an example of binaries, binary digit manipulation. So there it's always a good idea to see what you need, what affects what, which bits affect which bits, and what's the result, and that will get things organized in your head. Once you have that, you have to think about what you're going to implement and how you're going to implement it, and you're going to have to come up with your algorithm, with your solution. So this is up to you. This is the process. Google is a good friend in these cases to find solutions to problems you've never encountered before, and you can make up your own algorithms if you're good in that, or get your sources from all around. So it's good to break your problem into smaller problems. If it's a big task, it's always a good thing to break it into modules, into classes, into methods, into just see how things are constructed and how you can provide a well-structured solution. And breaking it down into the smaller bits always helps to build your solution from small. And because if you come up with a big chunk of code and just throw it into the screen, it's going to be hard to debug, it's going to be hard to understand, and it's prone to errors that are quite problematic in that case, and it ends up in a big block of spaghetti sometimes. So break it down is also a good tip. Testing, testing is always important in any case. Think about how you're going to test your code, and think about all the cases that your code has to cover. So in advance, if you have to analyze or process some numbers, think about the end cases and how your algorithm will behave in such cases. And later, when you implement, you're going to have to be testing and checking all the possible scenarios that you can think of, and then somebody will come and break it with some scenario that you didn't think of, and that always works. So that's an important tip. Efficiency, in small scale problems is something that usually wouldn't be such a big thing unless but it can be broken quite fast. We've been talking about the problem with in your sample exam, the one with the subsets, right? That's the most tricky one in there, because you cannot use recursion, and we're not going to talk about recursion until the next course. I don't remember. But just to demonstrate, by the way, do you know what happens if you write recursion in Google? Nothing. Could be that it works only in the English Google. Yes, it does. So for those of you who don't know what recursion is, it's exactly this. What will happen when I click now? I'll get into the same page, right? And now, into the same page. So we are defining recursion by recursion. So we are actually using the definition in order to step into a deeper definition, and then that could be quite endless. So there's the concept of recursion will be discussed more in greater details when you have to learn what it is and start using it. And some beginner programmers, from my experience as a trainer, have some problems grasping the concept of it. So Google is a good friend in this case too, just to give a taste of what it is. But recursion is an extreme example of very simple code that can become very inefficient in runtime. It could be very easy to implement certain solutions, but they could take a lot of memory. They could crash your memory, by the way, if your recursion is endless. It's not like an endless loop. This can get you into a very fast into a Stack Overflow, and can run your CPU high, and it can take a long time to process. So efficiency is something that to take into account when you are planning a big solution which can have such problems. Once you have it all structured and you think about how the implementation is broken down and you have a good idea of what you're going to do, then you can take the steps that you've made up in your mind and just pour them into the compiler, and hopefully there'll be very little errors to fix, but there will be. And once they're fixed, you have to start testing whether you're right or wrong and to fix your bugs. So that's basically the process broken down. Now we're going to dive a little bit into the steps and see them, and we're going to take one example and see how it works with it. By the way, any questions so far about this overview? So as I said, once you have a problem, first you have to analyze and well understand it and know exactly what you're facing. So they give here an example that you have 5 problems in 6 hours, which is looks like something that you might have in the near future. So first read carefully and understand the requirements. And there's a tip here: start solving the most easy problem first, but that's really up to you. If you have a test where every problem has the same weight as the other problems, so the score is distributed, you can start with the easiest one, so you can just use the time and get your scores and then go to the complex ones. But of course, if you want to do it the other way around, it's up to you. But you can get stuck with a big problem for a long time and not solve it and not have enough time to go to the simple ones that can get you the scores. So that could be a good tip at some point. And the other tip here is to take a problem one at a time. Take it, build it in your mind, understand it, construct it, think about its limitations, put it into code, test it, and once you have it complete, then you can move on. It's also good psychologically, because otherwise you'll be completely running back and forth, and your mind will be running back and forth. I think we have a visitor. So we are faced with we're faced with 3 problems here. One of them looks rather simple. We have a set of numbers, and we want to count how many times a certain number appears in the set. Then we have the second, take a group of students and find student with the highest mark. So again, this is just finding an element inside the set, or depends on the, again, this depends on the requirements. This could be something that relates to many students or many grades of students, where we have to start calculating the average of each one. So that's something to take into account. And the last one, which looks like the heaviest one and the one that we're going to look deeper into, is the binary problem. Like to count how many ones and how many zeros are in a binary representation of a number. So the third one looks like the more complex one, and we're going to dive into it. So first of all, reading and understanding, and we are facing here three. These are actually, let's say, the first reactions that can come to mind. So if we have a set of numbers, then we want to find a certain instance of a number inside the set. Just have a counter, right? Go through your numbers and have a counter and increase it every time you encounter the right variable. If you have the students and you want to find the one with the highest mark, let's say that it's a simple solution that we don't have to start calculating averages and things like that, and we have only one student per mark, then we can just save a temporary with the highest one that we've met so far, then go on, and once we find the student with a higher mark, we just change our temporary variable. And the binary representation, there could be many solutions here on how the program will behave, but we can count the ones, for example, and once we know how many ones, we can also infer how many zeros, even though we have to do it smartly. It's not that if it has 3 ones, it has 4 zeros necessarily. So, as I said, always have a pen and paper near you. It's not always used on my everyday, but it's almost always used when I face a new problem, and it gets things very well organized. And like it says, paper is faster, and visualization is much easier than many times I say, well, I won't do it with a pen and paper. I'll open a notepad and I'll write my things and I'll structure them, or with Word. That takes more time, and it's not very easily visualized. If you have code blocks, if you have some idea, if you have to start manipulating bits, it's easier with pen and paper. It's faster and it's much better visualized. So for example, if we have a binary problem like this, we can start sketching our ones and zeros, and we can see how we're going to take, for example, an approach of always checking the rightmost bit. And we're going, and we can see the number, and we can see how it's broken down and how we are actually counting the ones or counting the zeros. So that's already some kind of a organization of the solution in the mind. So that's always good, and that could be helpful, especially if you're in a test and you want to better understand how you're going to solve it and whether your idea is right or wrong. It's always good. Yeah, thinking about ideas is up to you. It's the endless pit, and you can come up with endless ideas. You can find ideas, you can look for them online, offline. You can take other ideas and reshape them, and that's something that is completely up to you. Just try to think whether your idea is covering all the scenarios according to the problem that you're trying to solve. So here we have, for example, 2 ideas how to approach the bitwise operations problem. One approach, maybe let's say the more intuitive one, the simpler one, is to try to take the rightmost or the leftmost bit of the number, check what it is, and then take the number and shift it either to the right or to the left, depends on what your approach is. That's simple, and I've seen some people doing it in the homework exercises, and that's a good approach. Another approach, which may be a bit less intuitive, is try to divide the number by 2 and check the remainder. That's because in binary representation, if we look at a number and it's an odd number, its rightmost bit will have to be 1, right? Because so we can check the remainder on dividing by 2, and we can see whether it's an odd number or an even number. We can divide by 2. So actually, once we are dividing by 2, since we're talking about representation of on the base of 2, then we get a shift, actually, because we are moving each one of the digits is on the power of 2 in the binary representation. So if the first digit is 2 on the power of 0 and the second is 2 on the power of 1, once we divide by 2, they are moved one space. So we get a shift. Get my shift? Yeah. Try to think about your solution, whether it matches the needs, whether it could look good, but at some points you can come up with problems that may occur, or where your solution doesn't match the requirement or can break. And these things are not easy to find usually unless you're in front of a computer. And I don't know how things are done here, for example, in the university where I studied. I don't know if they're doing here the same, but programming exams are always on pen and paper. They're never on a computer. They're here too like that, right? Yeah. So that's good, because once you're on a computer and things start failing, if you're on a pen and paper, you could have some errors and you can have some mistakes, and maybe it won't build, or maybe you'll have minor syntax errors, or maybe you'll have minor implementation errors, but your basic idea could be correct and it could be good. But if you're on a computer and you start debugging and you see actually, this doesn't work, but then you start fixing, but then you run into another bug, and then your syntax is wrong, and then you're actually breaking the algorithm, then you say, okay, I'll start over. And this can take much more time and can get you into much greater trouble. So checking it up first on your own, on paper, see whether it's a good idea to get some reference on your solution. Not always the best, but of course, if you are going to implement something, that could be a good step. And then when you get to the implementation, then you'll start the big time spending and seeing what's wrong with it. Yeah, what to do if your idea doesn't work? Well, try to fix it or try to invent a new one. That's a very helpful tip. Yeah, just invent a new idea. So good luck to you all. And carefully check your new idea, because you might need a new idea. And again, always go through and see all the cases, think about the problems, and good luck. Performance, as we said, could be effective if you are building something big, or if you're using recursions, or if your solution becomes quite complex. It could be good to check. This thing is not easy to test, but if you have some idea on a big loop, you can think about your input and you can think about how many times this loop is going to run, or if you can improve it, or if you can make it run less times. And one thing you can do is run your program with to make a load test and run your program with a lot of data and see if it takes too long, or if you can improve it, then you can run it again with the load of data, and you can see minor differences in the execution time. And that's something that could be that could be quite effective. Again, it's something to consider, but it really depends on your solution, and it's quite good to always try to load your code with a lot of data and see how it reacts. Yeah. It's good to run your code with big inputs. Try to see the whole range of input if possible. If you're looking for a 10 number or 500 numbers, try to run it with all of them. Try to see if your implementation works correctly, if it's efficient enough, even though sometimes you build things efficiently in code, but actually at runtime they could be quite cumbersome and slow, and the best solution is not always the most efficient one. And like it says, an ugly solution can work just fine. So this doesn't always correspond. Again, I come to the example of recursion, which could be quite elegant and small code, but it could rip your computer to pieces. So implementation. Again, this is all the checklist. Again, just before you start coding, that you have understood the requirements, that you have structured your idea, that you've tried to think about how effective it is and how good it is according to the requirements. And yeah, that's again repeating what we just said. Like I mentioned, taking a big block of code and putting it in just at once is always, not always, but almost always a bad idea. Breaking it down to the smaller bits is good, and it will help you also. Once you have it structured outside your compiler, it will be better. It will be good to be inside your compiler also written in chunks, and you can also test that these chunks are working correctly separately. So let's see a breakdown of how we start implementing the solution for counting bits of ones and zeros in a number. So we're starting with a sample number here, and we want to isolate the rightmost bit, the first bit. And the most intuitive, easy thing to think about is to just end it with 1, so that we'll get the rightmost bit end, which means that only this bit will be kept into our variable here. So if this variable goes to 0, this means the rightmost bit is 0, and if it goes to 1, then the rightmost bit is 1. Once we're done checking with this bit, we actually don't need it anymore, so we just shift our number to the right 1 bit. So this is what we're doing here. So that's a base step of the implementation. Yeah, take the rightmost and remove it. Okay, so we could check it on all kinds of numbers. So this step is one step in our solution. We could just try to run this code with a number or with a few numbers, and we can test that this thing actually works, that the bit is correct, and that the number is shifted correctly, and that's quite easy, right? Okay, so once we have that, we move to the next step. We have isolated the first bit of the number, and we want to see the rest of the number. So we've taken the rightmost bit, and when we shifted it, now we have to go on and continue our algorithm. But how long do we have to do this? Actually, at some point, all the bits of the number become 0, and that means that we have nothing more to check. So once we reach the last bit, which is labeled as 1, and we've gotten rid of it, the whole number becomes zeros, and we can check once our number becomes zeros, we'll stop our execution. So we'll improve our main idea. We'll add a while loop. So as long as our number is not 0, we're going to take the first bit, we're going to put it in a variable, we're going to shift, and we're going to write what bit we got in a new line. No, not in a new line. So we're getting this as we're going to 10. Actually, we're writing them from right to left. Yeah, we're writing them from right to left, but we're scanning the number from right to left, but we're actually writing the solution from left to right. So here we have 8 and 2, and that's it. But actually, the numbers that are represented here are a correct count of 1s and 0. Looks cool. So we need to start counting them. So we'll get a final count on how many 1s and how many 0s. What we have is 2 counters here, and we're just repeating the same algorithm of while. We're taking the first bit, we're shifting, we're checking whether it's 1, then we increment the 1 counter. If it's 0, we're incrementing the 0 counter. So we have a counter now. Testing it. Okay, once you write the code, see if it runs the way you want before you continue to the next step. Okay. So we want to check now whether our solution works on other numbers as well. So we'll put a bigger loop that will run through all kinds of numbers that we want to test. In this case, all the numbers from 0 to 5. And we're running this loop, and on every loop we're taking the number. Actually, we're reading a number from the console, and we're running our algorithm to count. And once we're done counting, once this loop is finished, we're writing down the 1s and the 0s. But surprisingly, this solution works badly. As you can see, it starts okay, but after the first, it starts going bad. The problem is, go back to the previous, is that we have put our counters outside our loop. So these counters start at 0, but we're counting for the first number, and then we're continuing to the next number, and these counters continue from their last count. So if we've found 5 instances of 1 on the first number, on the second number we'll start from 5, and we'll continue incrementing those counters. So that's a simple but commonly occurring bug that could happen. So to fix, in example, we'll just take those 2 counters and we'll put them inside the for loop. So every time we take a new number, we're resetting the counters and we are printing them correctly. Well, testing again, testing in that case could be important to test all kinds of numbers, positive, negatives, try to see where your limitations could happen, and try to think about cases where you could have problems or mistakes in your calculation. It's important to know that testing your code doesn't mean that it's bug-free, of course. As I said, you could test your code many times and still it would have problems that will be discovered later by you or by someone else, by QA or by a user, and
by the customer.
By the tester. Customer, yeah. These are the best kinds. Yes. if you're lucky, yeah, it'll be discovered by the customer, because that means you managed to sell something. And so yeah, it's good to have automation of your tests so that if you find the solution and you find a bug, you can rerun your whole set of tests again. Here, by the way, I can give an example that here our programs run, at least on our team on Sitefinity, which is a very big, complex product. We have, not counting what the QA does all the time and support people report sometimes problems, our code runs through 3 types of tests automatically. The first one is what we call unit tests. That means that actually the code is being executed and each of the functions in the system is being checked to see that it does what it expected on all kinds of cases, sending all kinds of variables and arguments to it and see that it responds correctly. Just the code block itself, not the product, not what the product does. So if I have a code block that needs to check how many ones and how many zeros are in a binary number, then this unit test will check only this block and try to see whether this block runs correctly. That's why it's called a unit test. The second thing is that we have UI tests. We have an automation system here called Test UI Studio, which is developed also by a different team in Telerik, and we are recording automation tests on our user interface. So this actually runs against the products and tries to click all the buttons and tries to see that the menus are not changed or the labels are not changed and the buttons are in the right place and that you can actually, the functionality is not broken at any time. And the third type of tests are integration tests that are running against the functionality of the system. So if we have an uploading system that we can upload files to, so it will try to upload a file and see whether this works correctly. So all these tests, which take quite a long time to run on such a big system, they are run on every new build that we are making, which means at least a few times a day, and those are automations. It's good to automate your solution. If you want to check for 100,000 options of numbers, you better build something that will run through them and run your code and test them. And once you have a problem and you check them, just make sure that your tests are running again, and all the tests, and see whether you've broken something or not. Yeah, if a bug is found, repeat all the tests to avoid regressions. Load tests, as I mentioned, run it on big data, see how much time it takes to run, and see if you can improve anything, and then you can run it again on big blocks of data and see, you can see improvements, because if you're running on a 5 milliseconds and then you're running another 5 milliseconds, it's not going to give you a clear picture. But if you run it on 100,000 input, and then you can see improvements on a bigger scale. And you can see how it works with big load. So if you're using a recursion with 3 numbers, that's one thing, but if you're using with 100,000, you'll see if it's broken quite fast. Well, of course, make sure that your solution is correct. That's, of course, connected to the first step of understanding what you have to do, and make sure that your output is correct. That's, for example, by the way, in the sample test, that I've seen some people putting console inputs and outputs, like nice ones, which are very, very well encouraged, like enter a number, or your number was this and that. But according to the automation testing system of the exam, you need exactly to follow the input and output as written in the tasks. So just make sure that your input, if it says input an integer only and output an integer, that will be just that. Just this input and that output, and no more outputs that can break it. So make sure that your solution is correct. Make sure that it corresponds to what it was supposed to give on any one of the scenarios. And yeah, again, all kinds of tests that you can come up with. That of course depends on your problem. Check with 10 numbers, check with 52,000 numbers, check with zeros, check with ones, check with all kinds of things which are borderline cases that could reveal some problems. So here's an example of running the algorithm with 10,000 numbers. Of course, we're not going to parse it from the console every time, but that could run quite fast, and that could be, like I said in one of the other lessons, I support programming laziness. I support scripting, making things run for you. I mean, that's one of the fun things of being a programmer is all about. I want the computer to work for me, so I write scripts to about pretty much anything that I need. So if you need to test, automation is a very good thing in this case. So you can build a whole test scenario here, either an array of numbers that could be affecting you, like all the borderline cases, or 10,000 or 100,000, and just let them run it once, and you'll see if you have problems. You'll see that more easily than doing it manually every time. So don't use the console, use an automation loop. And the results are, of course, perfect. Yeah, I think there's not much added. And we're here looking at the same slide of solution with a great number of trials. So that's about it. I just wanted to give a taste of, from my experience, a little bit on problem solving. And these tips are esoteric, but once you start, the more you work on computer problems, you'll see that they are quite useful, and that's actually the things that work best. Any questions about this? Any questions about something else?
During the exam, are we going to see our result?
I think so. I think it's going to be on the same system as the homework, the test exam.
Practicing like Vega Coder.
It's going to be on Vega Coder, I think.
And we can practice and see our little mistakes.
I think so. As far as I know, yes. Oh, it got unstuck. Hey, that's too bad. So I have, but I don't see it here. Yeah, these codes are almost the same. I just put small changes in them, but compilation failed. Yeah, for sure. Okay. I actually wanted to demonstrate all kinds of uploading scenarios here, and but I think it's quite easy and self-explanatory. Just if you're still working on it, as far as I understood, the system should be on until your real exam, or at least it should accept this until your real exam, because it cannot process more than one exam at the time. So. As far as I understand, it's going to be the same system. And just notice that since it's automated, since everything here is automated in the test process, make sure that your input and output correspond exactly to the solution, to the task, and just give exactly what you need, and you'll be able to see if it's good or bad. More?